We're going to find the interval of convergence again, and it's tempting to use the root test because these two terms have an nth power on them. However, this term down here doesn't have an nth power. I'm not sure I want to deal with that with the root test, so I'm just going to go ahead and use the ratio test. So we're going to replace n with an n plus 1, and we're going to put that in the numerator. And then we're just going to take that term and we're going to throw it into the denominator. As is pretty typical with these problems, we're going to divide these two fractions. So I'm going to straighten that out with a little copy dot flip. And once you do enough of these problems, you start to get the hang of things. We're going to take this 7 to the n plus 1, and we're going to think of it as a 7 to the n times 7. We're going to do the same thing with the x minus 2 to the n plus 1. We're going to think of that as x minus 2 to the n times x minus 2. And in doing that, we can cancel this 7 to the n with this 7 to the n, and this x minus 2 to the n with this x minus 2 to the n. That leaves us with a 7 and an x minus 2 in the numerator. And what I'm going to do is take these other n terms, and I'm going to put them together over here. Okay, let's shrink this down and get a little bit more room for this problem now. What I'm going to do next is I'm going to take this 7 times x minus 2 out of these absolute values. And when we do that, I'm going to keep an absolute value on my x minus 2. The reason I can pull this x out of this limit is because this limit has n going to infinity. N is changing with this limit. So x is a parameter that doesn't depend on n, so x can be pulled outside of this limit as if it was a constant. Now to find this limit here, we notice that the degree of the numerator is equal to the degree of the denominator. Our leading coefficients in the numerator and denominator are 1 and 1, so this limit is simply going to be 1. That tells us that the result of the ratio test is 7 times the absolute value of x minus 2, and we are wondering, when is this thing less than 1? Because when this is less than 1, the ratio test says that we get a convergent series. So we can start by dividing by 7, and we can rewrite this inequality as a compound inequality, and then we can add 2 to every piece of this inequality. And we're told that our basic interval of convergence is going to occur when the x value all the way up in this series up here is between 13/7 and 15/7. Now the ratio test is inconclusive if this limit happened to equal 1. So the ratio test tells us nothing about the endpoints, 13/7 and 15/7. So what we have to do next is test the endpoints by plugging those x values into this original series and seeing what happens. Plugging in x equals 13/7 gives us a series that ultimately reduces down to an alternating series, and the term inside this alternating series does go to 0, so we do get convergence. Because our series converges at x equals 13/7, I'm going to put an equal sign right here on our interval of convergence, and just one more step, we're going to test the other endpoint. What we get in the numerator when we do the simplification here is 1 to the n, which is just 1. So we have an infinite series of 1 over n plus 2. Now that is going to behave just like the harmonic series 1 over n. So this is going to diverge. To make that official, what we would do is a limit comparison test with the series 1 over n. What we would find is that these two series either both converge or both diverge. And since we know that this series 1 over n diverges, it's the harmonic series, then we know that this series also has to diverge. Okay, so ultimately what we found was an interval of convergence that includes 13/7, but does not include 15/7, and that is our final answer. All right, that was a pretty good one. I'll see you in the next video.